This is the video on roller coasters. This whole unit has been about energy. Energy is the capacity to do work. We've learned about like all energy are scalar, which means only magnitude, no direction. The unit for all of them is a joule. The four ways to store energy are potential, kinetic, internal, and rest mass. We're really looking at potential and kinetic. The law of conservation of energy basically states that energy cannot be created or destroyed. It can be transferred from one place to another, but energy can also transform or change into another form of energy. We've been looking at mechanical energy, right? Mechanical energy is the energy due to the position of something or the movement of something. Now, there are three forms of mechanical energy. You have kinetic energy, then you have different potential energy. So you have gravitational potential energy, elastic potential energy. Potential energy is the stored capacity to do work due to location in a force field. So we know that the equations are the three forms of mechanical energy, right? We have kinetic, gravitational potential, and elastic potential. Mechanical energies can be transformed into other forms of mechanical energy. In an isolated system, if there are no losses due to friction, then we say that the total mechanical energy of the system is conserved. A roller coaster is an excellent example of a transformation into one type of other. So the total mechanical energy does not change, but the different forms do change. So the original question is, why is the tallest point on a roller coaster the initial drop? So we did a simulation, when we did a bunch of different simulations. There we go, skip, skip, skip. What I wanted you to see is why the tallest point on the roller coaster is the initial drop, and it has to do with the gravitational potential energy. So if we look at something like this, right? What point on the track is the marble going the fastest? It's going to be at the lowest point because it's at the point where the most amount of gravitational potential energy is going to be turned into kinetic energy, right? Because the total amount of mechanical energy is the same, but as it goes down, that gravitational potential energy gets converted or transformed into kinetic energy. And kinetic energy is energy due to motion. Lowest point, you're going to have the most amount of kinetic energy. What point is the marble going the slowest? It's going to be point A, right? Very top. If it starts at rest or if it's rolling, it doesn't matter. The highest point is going to be the slowest point because that's where most of the mechanical energy is gravitational potential energy. I can look at this track and know that point C and E are going to have the same speed because they're the same height. Because that means that the same amount of gravitational potential energy has been converted into kinetic energy. So if I ask you to rank the points along the track going from fastest to slowest, you could easily do this, right? Lowest or the lowest point, highest point, right? So C and E are the same, then D, B, A. If I said go slowest to fastest, well, it's going to be A, B, D, and then C and E are the same. Now, without any external forces, will the marble ever be able to go higher than point A? Why or why not? The answer is no, because at point A, assuming it starts at rest, all of that mechanical energy is gravitational potential energy. And you can't create energy. It will never be able to go higher than that point because it would need more gravitational potential energy. So this is a good one, right? This is another example of a roller coaster. What point on the track is the car going the fastest? It's going to be C, the lowest point. What point along the track is the car going the slowest? Well, it's going to be point A. That's when it's at the highest point. What limits how tall a roller coaster can get? It's going to be whatever that tallest point is, right? Whatever it basically, it's basically going to be when all the mechanical energy is gravitational potential energy. That is the highest point at which it can go. Now, rank the points along the track. The car will be going fastest to slowest. So fastest, slowest, remember, lowest to highest. So it's going to be C, E, D, B, F, A. If I said slowest to fastest, it'd be A, F, D, E, C, right? Top to bottom. So it's real easy to be able to do this. No calculations either. Now, we already sort of answered this. Without any external forces, will the car ever be able to go higher than point A? This is assuming it starts at rest. Answer is no, because that's where all the mechanical energy is gravitational potential energy. To be at a higher point, you would need more gravitational potential energy. You need an external force. Why is the fastest point on a roller coaster the lowest point? We've already said that, right? And I like this one because this one does a really good job of visualizing it, right? So what type of mechanical energy does a car have when it's at a height? potential energy, gravitational potential energy. What type of mechanical energy does the cart have when it's in motion? Kinetic energy. Now, the two things that cannot be done with energy, you cannot create it, you cannot destroy it. So, and you can see in this graphic what happens as the mechanical energy goes up and down the track, the gravitational potential energy is transformed into kinetic energy. As it goes up, kinetic energy is transformed into gravitational potential energy. But notice what's happening. The total amount of mechanical energy is at 100, right? So what point on the track is going the fastest? It's going to be at the lowest point, right? Whenever it's at that lowest point, you can see all that mechanical energy is kinetic energy. What point of the track going the slowest is going to be at the very top of it, right? Because that's where the mechanical energy is the most amount of potential energy. And we've already answered this before. What limits how tall a roller coaster can get? Basically, you convert all the mechanical energy into gravitational potential energy. At that point, it would just come to rest, right? That limits how tall a roller coaster can get. Does mass affect the speed on the carts of a roller coaster? So this one, we need to be able to do some practice problems here. So I'm going to go ahead and shrink. There you go. That way you can see. I'll put myself up here. That way we can see the whole problem in its entirety. So this is a problem that we can have. A marble has a mass of 5 kilograms, starts at rest, rolls down the track, hitting the spring with the spring constant, 10 Newton meters. The height of the poles are HA is 20 meters, HB is 15 meters, HC is 5 meters, HD is on the ground, HE is the same height of HB, HF is 6 meters. Fill out the table below for all the points along the track. Then answer how far back the spring is compressed at point F when the marble comes to rest. And I give you, like we know that G on the acceleration of objects is 9.8. We just use 10 for G. Fill out the chart below for the mechanical energy at the different points along the track. So first thing that I want to do is I want to fill in everything I know. I know the heights and I know the initial velocity is 0 meters per second, right? Now what I can do is I know the marble starts out at rest at point A, so the kinetic energy is going to be 0. And I can calculate the gravitational potential energy. Mass times gravity times height. I don't have any elastic potential energy yet. Nothing's being compressed or stretched. And now to find the mechanical energy, I just add all three of those together. Notice what happened. You know, it's 1,000 joules of mechanical energy. I put 1,000 joules for all the points. The two things that cannot be done with energy, you cannot create it or destroy it. In this problem, we're assuming no losses to external forces, right? So it's not just these 6 points. It's every point along the track. I could make a chart 100 points long. I know the mechanical energy is going to be 1,000. So now what I can do is at point B, I can calculate the gravitational potential energy because now it's at a lower point. And I have 750 joules, mass times gravity times height, of gravitational potential energy. Now, how did I get 250 joules of kinetic energy? Well, these three, the kinetic energy, gravitational potential energy, and elastic potential energy, have to add up to 1,000. If I have 750 joules of gravitational potential energy, the rest of that energy is going to be kinetic. Notice also that when I filled in point B, point E also filled in the same amount. They're at the same height. They're going to be going the same speed. They have the same amount of gravitational potential energy, same kinetic energy. I can do that for point C, point D. Notice point D on the ground. The height is 0. All the energy is kinetic energy. That's going to be the fastest point. And I can do it at point F. Point F is a little bit tricky because now it's compressing the spring. Yes, technically that elastic potential energy is in the spring, not the marble, but we're just saying, hey, that's where that energy is. So it comes to rest when it pushes that spring back. I can calculate the gravitational potential energy. Now the rest is stored in the spring as elastic potential energy. So now what I can do is I can calculate the velocities. I know the kinetic energy at all these points. I can plug it into that equation for kinetic energy. I know the mass is 5 kilograms. I just solve for the velocity, and I can do that at all these points. Now, notice that, okay, B and E, that's a good check. B and E have to be at the same velocities. Let's see here. Point C, good, is going a little bit faster than point B. D has to be going the fastest. Point F comes to rest at that spring, so I know that they're at least in the right order. I don't know if I calculated it correctly. Well, I do know that these are correct, but that's just a good way to double check. You know where the marble should be going the fastest. You know it should be going the slowest. You know where it's at rest. You can do a quick double check when you're calculating these. So this is one problem. Let's do and that last point, you can plug everything into the elastic potential energy equation. As long as you know the spring constant, find out how far that spring gets compressed. Now, let's do another problem. This problem is exactly the same, except now I have a larger marble, 20 kilograms instead of 5. But the heights are the same. It still starts at rest, same track. So now I've got a larger mechanical energy, right? I've got a larger mechanical energy. I still do this spot because now I've got 4,000 joules of gravitational potential energy at the start. So I have 4,000 joules of mechanical energy along the track. So I can do the same thing I did with that last point. Now, here's the thing. Now I can calculate the velocities. Well, notice the velocities are exactly the same, right? The exact same. Even the heights are the same. Like everything in the problem is the same except for the mass of the marble. Now, yeah, that spring gets pressed back farther because it is larger mass, but let's see why the speed doesn't affect it. So let's take a look at a roller coaster and mass, right? So we know that the mechanical energy goes from kinetic or gravitational potential energy to kinetic, kinetic to gravitational as it goes up and down the track. We know we cannot create or destroy energy. Now, we don't have any elastic potential energy on this one, right? No spring, no compressions. Now, what I want you to see is that the mechanical energy at every single point along this track is going to be the same. And I set that in this equation here. The mechanical energy equals the mechanical energy, mechanical energy, mechanical energy. You could do this for every single point along the track. So now what I've done is I've placed the equations for those mechanical energies. I sort of expanded it out. So that's the equation for kinetic energy, gravitational, elastic. We don't have elastic potential energy in this, so those are 0. So this bottom line, which you'll notice is now I have the kinetic energy plus the gravitational potential energy is going to be the same at every single point along this track. Now, what you'll notice, mass is in every single one of these equations now, right? So at every single point, the mass does not change. The mass is going to cancel out at every single point. That's why the velocity is independent of the mass, because you only have kinetic energy and gravitational potential energy on this track. You add them together, it's going to be the same at every point. The mass is going to cancel out. That is why. Right? The velocity of the roller coaster is mass independent. So now we did this class activity where we calculated, where we did some problems where we calculated same thing that we just did in those 2 problems. We did them with several other problems. And just once again, remember, there's too much unknown in the universe to take a break from learning. Get out there and question everything.